we've got great pleasure in being joined tonight by Professor Serena Cussen. So I was going to talk to us about materials for energy storage, which I think is going to be a fascinating talk. So Serena obtained her BA in 2002, and then she got a PhD in chemistry in 2007 from Trinity College in Dublin. And the subject matter being new magnetic nanostructure materials. So there should be enough in here for all the materials people tonight for sure. She's then been to a tranche in terms of her career, a tranche of different universities, including California, Kent, Glasgow, where I believe you were the first female professor of chemistry. Wow. And then you've eventually ended up at the University of Sheffield, which is obviously the best city to sort of end up at. And you're the recipient of many awards, too many to mention, to be honest, so I'm not going to attempt to. So with that, if you'd like to start your presentation, that'd be great. Thank you.
Thank you so much. Make sure that everybody's okay online. Brilliant. Can everyone hear me okay on the microphone? Fantastic. It's such a pleasure to be here with you this evening, and thank you so much for such a kind invitation. You're going to learn pretty rapidly that I'm not a metallurgist. So it's especially kind of you to have me here this evening to just share with you a little bit about some of the research efforts ongoing at the University of Sheffield on energy storage, with particular reference to the transport sector. And what I thought might be fun to do would be to take a journey, not just through science, but through history, and talk to you about sustainability in transport from the Mary Rose to electric vehicles. And that's because a lot of the research that my group carry out at Sheffield is not just on electric vehicles and lithium-ion batteries, but also on conserving the artifacts that were saved from the Mary Rose hull. And the reason that a research group at Sheffield can do such a broad range of different applications is because we're material scientists and engineers. And so we have that depth of experience across different disciplines to be able to apply what we know to such a broad range of applications. So I completely agree that Sheffield is the very best place. And I thought I'd tell you why I think it's true. I have the pleasure of being the head of department of material science and engineering, and that sits within the Faculty of Engineering, where there's a huge emphasis placed on doing fundamental research that underpins engineering solutions that then have a positive influence on our planet. And that's something that I remember every day when I go into work, and it's so inspiring. That everything we do in our labs, we're trying to be working more and more towards a more sustainable future. And so on the days where the reactions don't work, or the journal writes back to you to say, no, not today, or your proposal doesn't get funded, remembering that everything you're doing is for the greater good actually makes you feel a lot better. So in my department, we have three main areas of research. They cover materials for extreme conditions, from aerospace to nuclear materials, to how to look after nuclear waste management, to looking at how we might get inspired by nature to make new lightweight materials. We also look at materials for society, and that's, I suppose, the area that my research sits in, looking at energy storage and conversion. But I've got colleagues who are making sustainable steels, sustainable cements, looking at how to make more efficient devices based on functional materials, to looking at how we look at manufacturing processes and make them more sustainable, less energy intensive and less carbon intensive. And then we also have a sector of the department that works on materials for medicine and health, and that's looking at more sustainable biomaterials or materials that we can use for diagnostics or antibacterial applications. And we do an awful lot of medical device development. Lots of clinical trials come out of the departments just up the road, which is really exciting. Lots of collaboration centres, partnerships that underpin an awful lot of this research. So if you haven't been into the university recently, we've just opened the Harry Greerley building, which is part of the Henry Royce Institute, and that's for advanced method processing, as well as people working on DNA, people working on batteries, people working on biomaterials. So if you're near the university, pop in and say, and be happy to show you around. On battery research or the Energy Institute at Sheffield, lots of fantastic research tools to be able to do all of this fun research. And all of this, I mean, I've sort of put the statistics in very small writing because it's not all about the statistics, it's all about the environment and the collaborative nature of what we do. Really proud to tell you that our department is #1 in the country for research environment and #1 in the country for student satisfaction and in the top 5 for materials in the Guardian recent league table. And all of that illustrates how exciting it is to be in that department. So with that, why am I here to tell you about transport? I'm going to start with the Mary Rose. Mary Rose, if you don't know it, was commissioned by King Henry VIII, and it was his flagship in his fleet. And it sailed for about 30, 40 years before it sank in with Solent. And this is the Cowdray engraving, which is the sort of a representation of what happened on the day. And I promise the Rose sinking. And for many, many years, she was lost. And it was not sure where her hull was. And it was in the mid-60s when a retired Marine officer, Alexander McKee, spearheaded the search for the Mary Rose. And in the late 60s, a sub was discovered. And in 1982, many people remember what he did this. She was taken from the seabed up on this yellow crane and then taken to a dry dock in Portsmouth, where she underwent about 3 decades worth of treatment to try to conserve that wooden hull. This is what a fantastic thing to be able to do, to retrieve this wooden hull from the seabed. This is what the Mary Rose looks like today. That's not it, that's the museum. If you ever get the chance to head down to Portsmouth and visit the Mary Rose Museum, please do. It's one of the greatest things in the UK. To head into this state-of-the-art museum, which is built around the hull, and within that, then you can actually be in the same room as feels like you're in the presence of history. And all along the sides here, these glass cabinets are many of the thousands of artifacts. 19,000 artifacts recovered from that treatment so that they'll survive for generations to come. And so this was my you can see that there's a stain on the wood, there's some regions of white. The wooden hull was made with a polymer called polyethylene glycol. And the job of polyethylene glycol was it was in 2 forms, short form and long form, ability to the ship. And if you have a look here, this is just showing you some of the artifacts that were retrieved and some of the treatments that these were undergoing. And you can see, for example, this is somebody painstakingly serving one of the so there's an urgent need for new treatments. Why is that? Well, if you waterlogged wood, they can come from chemical means, biological means, mechanical changes that happen over time. But in this particular case, there were a lot of iron fixtures that were present on the ship. And there's also lots of bacteria that live in marine environments, and they can act as sulfur-reducing agents. And when those sulfur-reducing bacteria meet iron, they can form iron sulfides. And all of this is jolly interesting for chemists. But when that stuff is under the water, if it comes up into an oxygen environment, It then oxidizes to form acids, and that's where you have a big problem. You could potentially be forming acids in that wood that could then damage the wood even further. So part of the challenge is to try to address this sulfur problem in Mary Rose wood. One of the ways you might be able to do that is to remove the iron that's catalyzing the formation of these acids. I'll show you some ways in which we've been trying to do that. So if we try to look at the structure of Mary Rose wood, you can use lots and lots of tools, right? You can use X-rays, for example, and you can use scanning electron microscopes, such as this image here is showing. And I can use X-ray, secondary X-rays that come off that to give me some idea of the elements that are present. And so from this kind of experiment, I can tell that, well, I've got some sodium in there. Okay, well, there's lots of sodium chloride, you can see. I've got some iron, and I've got some sulfur, but I don't know the structure of these materials. And that matters because if I don't understand the structure of what's in there, how can I design a treatment that can then remove those harmful species from the wood? So, looking at something like waterlogged wood that's been under the water for hundreds and hundreds of years, it presents a big challenge. This is a really, really heterogeneous system. You've got the wood itself, you'll have some crystalline bits and pieces that are within that wood. You can have amorphous materials that have no long-range structure. You can have little bits of nanomaterials floating around in there. Lots and lots of different sizes of materials, lots of different natures of materials. So what we need is a technique that allows us to tell all of those structures apart. And so we went to the ESRF, the European Synchrotron Radiation Facility. This is a picture of my students in this art, and this big round circular building here, that's the ESRF. And we go there to use high energy X-rays, and they allow us to get, in this particular instance, we combine it with tomography to get quantitative information, so we can actually tell the structure of these materials. And we can also tell where they are because it's a tomographic image. And so we collect these data, and this is just a picture of us doing these. This is Kirsten Jensen, who's now a professor at Copenhagen. In the background to the right is Professor Eleanor Schofield. She's a deputy director now of the Mary Rose Trust. And then I'm there in the background. I'm sort of standing like this because in that picture, I'm about 7 months pregnant. So I'm sort of waddling around this X-ray facility. I love telling people that because if you are a young female and you want to go into a science-based, lab-based career, having kids is not an impediment to doing that. So please do remember that. So what do you get when you do these experiments? Well, here's a picture of a little piece of wood that's taken out of the Mary Rose, just bored out of the side of the ship. That's the top of the wood that would have faced out into the sea. And then this is a piece of wood going in about 8 millimeters into the depth of the hull itself. And this is just showing you an electron density map, and that just allows us to look at the mesostructure of the wood. And what we can tell is, in these red regions, these are pretty dense. And then in these blue circular regions, this is where you've got pores that are present in the wood. This strange looking line is an artifact from how we put the data together. But what we can do is, and what's slightly difficult to appreciate from a slide is, this is a tomographic data set that's in 3 dimensions. So every single little box here is a voxel, a 3-dimensional voxel. And so we can select one of those voxels and find out what's the structure of the material in that voxel. So if I look here, this is wood. So I'm going to look in that voxel there and figure out what the structure of Mary Rose wood is. And that's what this pattern here is showing. And when I look at this is a total scattering pattern. What that is very often we use X-ray diffraction. X-rays come in, they diffract off our materials, and we can tell the structure of that material. That's really nice if you've got a beautiful crystalline material that repeats nicely, over infinity. If you've got teeny tiny bits and pieces within a degraded piece of wood, you're not going to have that beautiful extended crystal pattern. You might just have very short range where order exists. And that's happened here. You've got this short range where order exists. That's what these sharp peaks are telling us. And then that order just sort of drops off because everything at higher distances, this is angstroms, there is no order at those higher distances. But what this tells us and what we can do is fit these data sets with a model that we know is true for cellulose, for wood. And we can actually tell that this is the cellulose structure. So now we know what the structure of wood in the Mary Rose sample looks like. So if we know what wood looks like, we can figure out what not wood looks like, if that makes sense. So we're on the hunt now for things that could damage Mary Rose home. And that's what this is showing you. We've basically mapped onto this the structure of wood, and we've located everywhere in this sample that correlates very, very highly with the wood or the cellulose structure. Anywhere that isn't red, therefore, does not correlate well with cellulose structure and is something else, something different. So, for example, this region here, that's a pore. That shouldn't be wood at all. We can use this as a test, please. This region here, number 2, that's also a pore, but it looks slightly different colours, this one. So there might be something else in there. This is a green pixel, it's something to do. And down here is a yellow one, that's something else as well. So let's take a look at the structures in each of those areas and see what they are. Well, it turns out we're able to locate this whereabouts in the wood this polyethylene glycol resides. And that's really fantastic because polyethylene glycol and carbon and hydrogen, very similar to cellulose, but we can tell the two apart using this technique. And this is the first time we've been able to locate how far into the wood over those 30 years spraying that polyethylene glycol has managed to penetrate. That's really useful because, unfortunately, polyethylene glycol can break down over time to form acids itself. And so this is now a new conservation challenge that people are facing to try to locate whereabouts that polyethylene glycol may be breaking down. And experiments like this, they're pointing people in the direction of areas where they might want to focus in on the ship. Very cool though was being able to locate these little red dots down here. And these were iron oxide, or sorry, sulfide nanoparticles with zinc contained in them. That we'd never known that there was zinc within Mary Rose wood until now. And so this has been a really, really interesting, really fantastic find because now we have the structure of what these potential acid forming materials look like. They look like iron, zinc, sulfides. And now we can start to design materials that could selectively target these nanoparticles and draw them out of Mary Rose wood. So why are we getting zinc in there? It could be in different reasons. There could be zinc deposits nearby the wood at some point, or there's bacteria that exist in marine environments that actually do react with zinc to form zinc sulfide nanoparticles. So it may be that you've got some sort of biological activity that's acting on zinc in the seawater and depositing it into the wood. My collaborator, Dylan, he works at Columbia University, New York, elegantly put it as this is bacterial poop that exists in Mary Rose wood in one of the interviews we gave about this work. But it's really interesting to know that we can determine the structures of some of these degradation products and then start to look for ways to remove them. And that's what we've been doing recently. I've gone back to my PhD and I found those again, really tiny magnets, which I can functionalize the surface of with agents that can selectively bind to this. And so in this case, what I wanted to try to investigate was an iron oxide. Oh, sorry, I've done exactly the thing you told me not to. Oh, microphone. Can I take some iron oxide nanoparticles? Can I coat the surface of them with some sort of receptor that can bind to iron, for example, so the thing that catalyzes acid formation? And I apply this to the Mary Rose Holland particles inside polymer gel, a bit like a face mask. And we then change temperature by just a degree or two, and this gel turns into a liquid. And in that liquid state, releases these particles that can enter the ship, spend some time incubated within the wood, try and latch on a bit like a Pac-Man to these free iron ions, and then we can use a magnetic field to then draw the particles out. And if we change the temperature back again, we can turn that liquid back into a gel and just peel it off the ship. So this is all the stuff that went into the proposal, but it actually worked. I'm not going to spend time on this. This is just the chemistry. This is how we made the stuff. This is a sample of the Mary Rose wood, and that darkened region there, it's dark because there's lots of iron present in this particular piece of wood. That shiny black blob is your iron oxide nanoparticles, and by using infrared spectroscopy, we were able to locate where we have the iron bound to a porphyrin, which is what we used as our sort of binding agent on the surface of these nanoparticles. So this has been a really fun project, learning lots about Mary Rose, learning lots about conservation, learning lots about how to come up with sustainable solutions to maintain these priceless artifacts. But some of the techniques that we've been using to understand the nature of deposits in Tudor wood, we're also using to understand how modern day batteries will now power electric vehicles today. And so I wanted to spend the last bit of my talk telling you a little bit about some of those results and what we're doing to try to understand how batteries work. So electric vehicles, I'm going to click on the chat here just so that it'll disappear. Brilliant. Electric vehicles are not new. In the 1900s, there were electric vehicles in the US, for example. President McKinley, when he was shot, wounded, he was taken to hospital in an electric ambulance. So these are not new. And at the time that they were around, Thomas Edison, this is a quote from him, he said, electricity is the thing, no whirring, grinding gears, no dangerous and evil smelling gasoline, and no noise. So it sounds fantastic. But with the birth of combustion engines, these took off, and that's why we ended up with combustion engine vehicles. But now we're seeing a return to electric vehicles as well, just take a march towards net zero and removing our reliance on fossil fuels. So if I look at the average CO2 emissions, this sort of paints a picture for why we need to move to electric vehicles. This red dotted line, these are our historical emissions, the blue line. The red dotted line is the target. This is where we should be if we're going to reach the goal of 67 CO2 per kilometre by 2030. And what this is showing is we're off target. Okay, we're not as low in this graph as we should be. So we definitely need to use something that's going to decarbonise transport if we're going to reach this goal by 2030. The other thing that this graph is showing you is that the technology decisions that we're making today, the fundamental discoveries that are happening just up the road or in other universities around the country, those discoveries have to be made today in order to be of use in 2030. It takes that long for the discoveries we make now to actually bear fruit and become industrially relevant and scaled up. The sorts of things that as somebody who's on the very early stage of designing materials and making them in, maybe I might make a kilogram of something, I want to automatically appreciate the challenges of scaling that up to to tons and tons of material. So it's really, really important that we're doing all of that fundamental research today so that we can address some of these challenges tomorrow. The other thing is electric vehicles for the UK are expected to grow quite a lot. So if you look at this graph here, it's showing you what the market share of electric vehicles may be in the UK by 2040. And we're expected to need between 1.1 and 2 million electric vehicles by 2040 per year. So that's a 1.1 growth per annum between now and then. So there's a definite need for electric vehicles, and there's a definite need for batteries. And so if the UK is to supply the batteries required to meet this demand, we're going to need the equivalent of 8 gigafactories to be able to do this, to address this. So again, the need for a skilled workforce, people who know how to make these materials, how to assemble batteries, how to test them, how to make them safe. This is all vital. And also, what do we do at the end of the life of these batteries? Do we recycle them? Do we put them into some other second life that we can derive more use out of them? In the UK, there has been a huge investment in battery research through the Faraday Battery Challenge. And I have huge pleasure being part of that. So I run one of the large battery consortia for the Faraday Institution on next generation cathodes for lithium-ion batteries. We're called FutureCat. And so what we're trying to do is design, develop, and deploy the next generation of battery cathodes for lithium-ion batteries. What we really want to do is to try to improve things like the energy density of your battery pack. So that's a measure, I suppose, of how far you're going to be able to drive on that battery in a particular charge state. We also want to be able to improve the power density. That's how fast you can charge, how fast you can accelerate. We want to be able to reduce the cost. They're very, very expensive. So can we stop relying on toxic, expensive, morally questionable, hard to access elements? And can we look at more earth abundant alternatives? And also, can we improve the lifetime of these? Can I promise you that in 20 years' time, these batteries will last the lifetime of the car? So these are the sorts of questions we're trying to address. So my project is led out of Sheffield. We're joined by researchers in Cambridge, Oxford, UCL, Lancaster, and the Warwick and the ICIS Neutron and Muon facility. And we're about 65 people across the UK. We've been working on this for about 3 years now. And we're continuing to work on it for the next few years. And there's lots of other projects as well. There's projects looking at developing recycling infrastructure in the UK, because one doesn't exist at the moment. And how do you develop the policy that goes along with that? There's one on sodium-ion batteries. How do you move away even from lithium to something more sustainable? Solid-state batteries. How do you move to more safe solid-state materials that don't rely on flammable liquid electrolytes? So there's lots of different projects ongoing. Then that fundamental research is then brought through to industry by looking at funding that's specifically for demonstrations or sort of moving from lab-based activities up that sort of technology readiness level pathway to try to pick some things that might actually have impact on industry in the future. And the other part of this is the UK Battery Industrialisation Centre, which is down in Warwickshire. And this is where you've got an open access, like a microfactory, where you can go and you can build large amounts of battery cells for large scale testing. So it's a really exciting time to be part of the battery research community in the UK today. So when I say battery and I say charge and discharge and I use words like energy density, what does all of that mean? I thought it might be fun to go inside a battery cell and think about, what do all these processes mean? What's happening when I plug my phone in at night and I charge and discharge it? So this is a coin cell, and you find them in the back of remote controls and things. And if I was to chop that open, but don't chop it open, if I was to take a cross section through this, I'd see that I have a layer that we call the anode and a layer that we call the cathode. And they're the negative and the positive side of the battery respectively. And keeping them apart from each other is a separator. And that separator is soaked in a liquid electrolyte. So typical cathodes look like this kind of structure here. This is lithium nickel manganese cobalt oxide, which I'm going to say, you get NMC. And sometimes you'll see some numbers at the end of it, like 111 or 811 or 622. That's just telling you the relative amount of each metal that's present in there. And typically, the more nickel you have in there, the higher the energy density. But the higher the nickel you have in there, the more challenging it is to make. And it can undergo a lot of degradation processes. But the thing to notice about that structure is it's layered. You've got these beautiful layers of, in the blue there, some metals bound to oxygen. And then in the green, those little green spheres are lithium ions. Now that's what a beautiful crystal structure looks like when I plot it on my computer. In reality, sometimes those metals sit in the wrong spot, and that can lead to challenges when you're trying to charge and discharge your battery. So that's part of the reason we do a lot of research on how to make materials better, to try to get a bit more control over that order. So what's happening when I'm charging and discharging my battery? Well, there's lots of chemical reactions that are happening within that battery, and it leads to a buildup of electrons at the anode. Now, those electrons are not allowed to go back through that battery into the cathode. What's stopping them doing that is the electrolyte. The electrolyte is there to only allow ions to move through, not electrons. So those electrons are forced out through an external circuit, and they go off and they do whatever work they do, and then they re-enter into the cathode. And then your cathode has some redox reaction. And at the same time that those electrons are moving in that external circuit, you've got lithium ions moving in the opposite direction. So what's happening is you've got these lithium ions that are between these metal layers, metal oxygen layers in your cathode. And during charge, those lithium ions are transported across that electrolyte, and they sit between the layers of the anode. In this case, the anode is graphite. These are just layers of carbon atoms in between which the lithium ions reside. And then once your battery is fully charged, you can discharge it, and those lithium ions move back across the electrolyte back into the cathode. And this is a reversible reaction, so it's a rechargeable battery. So the history of this is in the 70s, Stanley Whittingham was working on compounds that look very similar. These layered materials, these are titanium disulfides. And so he was looking to see, could you potentially use these as battery cathodes, but it proved that these sulfides were not particularly stable. And so around about the same time, John Goodenough in Oxford was looking at, could you look at oxide materials? Could they be more stable? And this really was coming at it from a solid state chemistry point of view and looking at the energy of your cobalt and your oxygen, and whether or not you could make a compound that had lithium in it, and then you could extract the lithium and charge and discharge that way. And then Akira Yoshino had thought about using graphite as an intercalating anode, intercalating meaning that you can slot those lithium ions into and out of that structure. And it was just a few years ago that all three were awarded the Nobel Prize in Chemistry for the development of lithium-ion batteries. And it was such a wonderful recognition of something that's really changed our lives. They're ubiquitous now. I've mentioned this already. These are the kind of targets that we're trying to address. Things like reduction of cost, improvement in energy density, improving power densities and lifetime. So I'm going to sort of move on to what we do in Sheffield. We make a lot of materials in the materials department of Sheffield. So we look at things like, how does synthesis and how does what we do in the lab influence the final properties of a material that we then want to use in a battery? And it turns out it has huge influence over that. So I'm going to show you some examples of ways we make things and what the output or the impact of that is on the performance. So sometimes we use traditional methods like solid state ceramic methods. And that's where we take materials, solid materials, we mix them together intimately. So really like grind them together so that they're touching and they're really, really, really well mixed. And we use elevated temperatures to essentially get these two solids to meet, mix, marry, and form whatever compound we want in that interface. So it requires a lot of heat, a lot of time, it's very energy intensive, but you get beautiful big particles. And this is showing you an X-ray diffraction pattern of what particles like this look like, really beautiful sharp peaks that tell us these are really, really crystalline. And by doing this kind of method, we can systematically change things like how the chemistry of these materials exists. And in this particular case, we were able to change, in this material, it was a sodium ion electrolyte, so something that allows sodium ions to move through it, but is not a liquid, it's a solid. And by doing that, we can lower the activation energy that sodium ions need to be able to move. So this was really great. You can also think about, how do I change the size and shape of things? So I can sometimes use a liquid in a solvothermal type synthesis. And this is showing you a liquid-based reaction where we're able to make nanoscrolls of a vanadium oxide material. And by just changing the reduction conditions, we can form very small nanoparticles, in this case of V2O3. And that can change the electronic properties of these materials because the size has a big effect on the properties. Increasingly, I mentioned that we're trying to make these in a more sustainable way. We're trying to look at less energy intensive methods. So my group have been increasingly looking at microwave synthesis as a way of driving down reaction times, reaction temperatures, and energy cost. And so we've been doing that by selecting materials that can react very efficiently with microwaves. So they couple really nicely to microwaves. To do this, you need to have a material that's got an electric dipole. And because the microwave field is an oscillating field, that oscillating field can interact with that dipole and basically make it turn around and back and forth as the field oscillates. And that can set up some localized heating. So in effect, what it means is your whole reaction heats at the same rate, so you have no temperature lag across it. So I get a lot more control over my reaction, less chance of atoms being really naughty and sitting in the wrong spot. And that's what this is showing you. This sort of experiment here is telling me that the atoms that I'm expecting to be in the lithium layer are in the lithium layer, and the ones I want in the metal oxygen layer are there. They haven't swapped places. If I do this reaction not using microwaves, that's not the case. I get lots and lots of disorder. I also use co-precipitation methods. So this is where if I want to make something quite complex, like this lithium nickel manganese cobalt oxide or NMC material, I can add together all of the constituent parts. I can really tightly control the pH, the stirring rate, and what else am I? The temperature, lots and lots of parameters that you can start to refine here, so that you can actually develop assemblies, spherical assemblies of individual particles that aggregate into these large spheres. That's really important because these are the kinds of arrangements that give you high energy density in lithium-ion batteries. So being able to control that is really important. The other thing that we can do is we can make crystals of these materials. Why would we want to do that? If you look at something that's polycrystalline like this, where you have all these little primary particles dotted together in a secondary assembly, every time lithium moves in and out of that structure, these particles, their volume can change ever so slightly. So these are constantly changing volume. And sometimes that can lead to a crack through that particle. If you use a single crystal, you're less likely to get those cracks. And so you may have seen some news stories a few years ago of the million mile battery. And that was based on these sorts of single crystals used for nickel-rich materials. So why are we focused on the cathode? Well, the cathode, or the positive end of the battery, it's the most expensive part. So Exawatt is a local company here in Sheffield, and they're very famous for looking at market analysis of PV materials, but increasingly they're looking more and more at battery materials. And their research has shown that if you break down the cost of an individual battery to its specific components, almost half the cost is dedicated to the cathode. And so that's why we focus so much on this. If we can make one new cathode material that is made from sustainable elements that can be recycled, that are not expensive and toxic and hard to find, we could make a huge impact on the cost of batteries as there's more and more uptake of electric vehicles. So that's one of the key things we're trying to do at Sheffield. We're doing this by looking at how do you control, for example, how do you control the synthesis of materials so that you get it right first time? that we can target specific morphologies and specific chemistries using known standard operating conditions, so that we'll get the same result every time, and we'll have confidence in the sorts of chemistries that we're developing. So we've been making these sorts of new assemblies of our particles. We've learned a lot at Sheffield about how to control the synthesis so that we don't end up with any gaps in between particles, which can often happen. And you can imagine those gaps acting as sites for potential cracking to occur in these high nickel content cathodes. The other thing we're doing is, we're not just looking at morphology, we're also looking at the chemical structure of these materials. So sometimes, I've mentioned that lithium, it might not always go back into the position it should go into. Sometimes these metals swap places. We do some neat tricks with the chemistry here, where sometimes we'll replace some lithium and we might put some magnesium in there instead. And the magnesium acts like sort of a stilt or a crutch. It pins these layers in place and doesn't move. And so you end up putting almost like struts into your chemical structure to keep those layers in place. And what we find is that although there's not as much lithium in there anymore, we get an awful lot more lifetime out of these batteries now, because we're keeping them, the structure more, it's more robust structure. The other thing we're doing is, and this is another neat trick, is we can take particles that are nickel rich. So remember, this increase in nickel means an increase in energy density, but it can also mean an increase in reactions, side reactions that you don't want to happen. We've been able to grow materials where in a single particle you have a nickel rich core and a manganese rich surface. It sounds a bit like box chocolates, with sort of like these centers that are really great, and then these protective outer casings. But that is essentially what we're doing. Why are we doing it like a gradient? Well, if we did it like a coating, you could potentially have an issue of delamination of your coating. And so we try to avoid that by tuning the chemistry so that we very gradually introduce manganese onto the surface. That's what this picture is trying to show you. That darker orange is gradually coming into the surface of those particles. And what we see is this black line is telling you the capacity, which is the amount of charge under certain conditions that your battery is storing over many hundreds of cycles. This is commercial materials, and so you lose capacity over time. And these are our concentration gradient materials. They retain capacity for much, much longer than commercial materials do. So we're working at the moment to scale this sort of chemistry up so that we can make many, many kilograms of material that we can then pass to our friends in Warwick, who can do some large-scale batch testing of these batteries. We're also looking at making high nickel content crystals so that we can try to avoid this cracking phenomenon that can occur. This is showing you really nicely what I mean by that. This is a very similar experiment to what we did on the Mary Rose. This time we're using fluorescence with combined with X-rays. This is showing you some of those spherical materials that we had, these high nickel content cathodes. And after 500 cycles, it's all broken up into little pieces. They tend to fracture, put them under quite a lot of pressure. This is showing you the same kind of cathode, but now it's a single crystal cathode. And you don't see those dark gaps between the particles anymore because they're not cracking as much. And in fact, you find that you get better capacity retention over many, many hundreds of cycles by using these kinds of morphologies. So we've been looking at materials that are that have ever-increasing amounts of nickel that deliver ever-increasing capacities or energy densities. So you can see that for this particular material, this is this NNC 811. So the ratio of nickel to cobalt to manganese is 8 to 1 to 1. Ideally, we would completely remove the cobalt. Cobalt is very expensive, it's very toxic. Most of it comes from the Democratic Republic of Congo, where there are no child labor laws, and there's huge ethical concerns about the mining practices for cobalt. So These articles challenges of cobalt, and ideally we would like to replace cobalt with another element that can do our job, structural stability, and reduce our reliance on these kinds of challenging elements, and ideally move to something where we're just using lithium nickel oxide. This is a challenge because nickel oxide isn't always very stable, but we've been able to do some tricks in our labs in Sheffield and around the country to generate single crystals of lithium nickel oxide that are giving us huge improvements in capacities. And we're starting to see how we can maintain those capacities over time by looking at the chemistry again, trying to stabilize those layers and to introduce concentration gradients at the surface. The other thing that's really important, and I don't have to tell a group of metallurgists this, but the mechanical strength properties of these things really, really matter as well. And so if we can try to come up with a set of design principles around what sort of particle sizes should we target, what sort of particle target, so that we've got the most mechanically robust cathode, so that when it comes to manufacturing the just during the manufacturing process. We've been doing lots of operando kind of experiments. This is done by Professor Beverly Inkson and Dr. Laura Wheatcroft at the University of Sheffield, the Materials Department. This is in a scanning electron microscope. They're using a nano indenter to press down on one of our single assemblies of our particles to try to work out the mechanical properties of those individual cathodes. And what he's able to show is how those cracks penetrate through those secondary assemblies. And the other thing that about is we've also given them cathodes, starting to understand the mechanical properties now of cathodes that have been put under an awful lot of pressure. They've done an awful lot of work. And so we're starting to learn, only recently starting to learn a lot about how to optimize those cathodes now. Cracking and against fracture. Mentioned reliance on very expensive or toxic elements. One of the things we're trying to do is look back to the periodic table of elements and start to look for elements that are more earth abundant that we might try to rely on in place of some of the things. So you see here, for example, cobalt is here in orange, as a rising threat to increased use. Whereas nickel's in yellow, which is just limited available future risk to supply. However, in recent weeks, recent months, the price of nickel shot up. It was over 100,000, and that was as a result of the Russian incursion into Ukraine. And so supply chain issues with nickel are becoming an increasing challenge that we have to face. So how do we reduce our reliance on these things, but still get the same performance? So we'd ideally love to move to something like sodium instead of lithium, lots of sodium, maybe iron instead of cobalt. So I'm going to show you some examples of this. One of the cathodes that's a very good structure called olivine, it's lithium iron phosphate. And this is one of the cathodes that is currently under in Tesla. It was part of the Tesla future plan. They did World Tesla Day last year, and lithium iron phosphate is one of the cathodes that was being touted as being very, very useful. It's also used in some other electric vehicles as well. Why? Well, if you look at the structure, these lovely blue arrangements here are our iron surrounded by our oxygen atoms. These green spheres are our lithium ions. They sit within these beautiful channels. And then you have these lovely tetrahedra. These are our phosphate groups, which sort of bridge the iron atoms and add some structural stability to this whole thing. So it looks wonderful. All those lithium ions can move in, move out of that spot quite nicely. The only problem is sometimes when you have one-dimensional diffusion like this, if an iron was to sit where a lithium is, this would be called an anti-site defect. And that channel is now blocked and can't be used anymore. And that limits your capacity. So we need to try to find ways to make materials that resemble this kind of structure, less defects in them. And that's what we've been doing. We've been using, this is a microslicer over here. It's not like the one in the kitchen. And we can control the pressure of this quite tightly. We can control the temperature and reaction times. The volume of material that we put in here, space pressure can drive your reactions to alternative products if not careful. We've been developing microwave chemistry routes to cathodes for about 10 years now. An example of how we've done this with lithium iron phosphate. We've made very small nanoparticles of lithium iron phosphate, which we then coat with a very, very thin carbon coating. Lithium iron phosphate is not very electronically conducting, so we add the carbon to improve the electronic conductivity. And what we find is that we get really great performance. And what do I mean by that? The theoretical capacity, if I was to calculate for all of those lithium ions to depart that lithium iron phosphate, the theoretical capacity would be 170 on this scale, milliamp hours per gram. We're getting close to 160 milliamp hours per gram for our materials. And this C rate is telling you fast we're charging and discharging that battery over an hour. So the higher this number, the faster you're charging and discharging over an hour. So 20 times over an hour, charging and discharging in a matter of minutes. And you're still getting very good capacities, even at those very high charge discharge rates. So even after 200 cycles, we're not seeing any depreciation in capacity. And when we look at this material after we've cycled it like this, we find that the lithium and the iron don't start to exchange positions, they stay where they were meant to be. So we think this way of making materials is really neat. It also takes 3 minutes, down from 24 hours. So we can make the same very high performance materials in very, very short amount of time. At the moment, we're only making a gram of it. We haven't tried to make any more. But the challenge now will be to move to scale. And that's what our next big project is looking at. Is we could think about, well, iron is great, lithium is great. What about sodium? It's just sodium instead. The answer is you can. Real benefits here of lower cost, low toxicity, lots of sodium to be had. If you look at the structure, it's ever so slightly different though. So now you start to see that the lithium ions are they're blocking the lithium channels now. So it's not, I'm sorry, sodium is here still in these channels, and the phosphates are also in the channel. They're blocking the movement of these sodium ions. So, and that long distance between sodium is actually impeding that hopping that needs to happen. So for these things to be ionically conducting, the ions need a spot to jump into. And so they need something to get out of the way so they can get into that spot. So in this case, that's very, very difficult. So what can we do? Well, we can beat it up a bit and make it a little bit more disordered. So I've talked about order being really important. In this case, it's the opposite. If we can introduce some disorder, now we've got lots of potential pathways that sodium can move around, and you can start to get pretty good capacity out of these materials. I'm not going to go through this in huge detail, but again, it takes about half an hour to make this material. We grind it up for a couple of hours, and we end up with capacity close to theoretical capacity. Theoretical capacity here about 130 milliamp hours per gram. We're at about 100 milliamp hours per gram. So we're increasing the performance of these materials by sharpening our synthetic pathway. The last thing I wanted to tell you about was solid state electrolytes. So everything I've told you about so far will use a liquid electrolyte, and liquid electrolytes are powerful. And so you'll have seen on the news sometimes these kinds of pictures where you've got Teslas on fire, or airplanes being grounded because of fires, or phones going on fire. That's down to very often the electrolyte. And so if we could replace the electrolyte with something that's a solid, that's a ceramic, then we could go to very, very high temperatures and not be worried about flammability issues. The only challenge with that is, I mean, there's lots of challenges with that. Great positives, you know, it could be very stable. All the additional bits and pieces inside a battery cell, like the separator, the solid electrolyte, could do that job. The challenge is conductivity. If you imagine two solids, a cathode and a, for example, and a solid electrolyte, you're asking them to meet and marry and to like it, so that in such a way that it facilitates lithium or sodium ions to move between the two. And they may not like each other very much. They may not be particularly compatible with each other. You might have, for example, a sort of lattice mismatch where, okay, lithium ions are quite happy moving through this material, but once they reach this one, not so happy, they've got to move around it. So if we can try to engineer materials that are compatible with each other, not just in terms of their chemical stability, but also in terms of the resistance to ion movement across interfaces, then you could potentially look at a material that, or a device where the ion mobility is sufficient that you can have an all-solid state battery. We've been doing this in two different ways. We've been taking solid electrolytes and forming a tiny, thin, almost nanoscale coating on the surface of cathodes to try to make that coating very intimate and so that you've got very good surface coverage. The more interaction, more sort of interaction you have between the cathode and the solid electrolyte, the more chances you have of lithium ions being able to move between the two. The other thing we're doing is we're designing our cathodes and our electrolytes to have very similar crystal structures. If they look very similar, then when we kind of click them together almost like Lego, they might fit quite nicely, and then we might be able to get lithium transporting across that interface. So we've made a few examples of these recently. One is this really beautiful material that we made by accident. And this was made by a PhD student who was trying to make quite a complex material, a garnet, but instead came across this material where lithium sits on two different sites. And because of that, you've got multiple lithium pathways through that material. The metal here, by judicious choice of that metal, you can end up with something that's redox active, so it can act like a cathode, or something that's non-redox active, but is ionically conducting, and that can act as an electrolyte. We've also made some phosphate-based materials that are based on an acetone structure. And again, just the choice of that metal means that you can either be a cathode, or you could be an anode, or you could be a solid electrolyte. How do I know that these things actually allow for lithium diffusion? And I'm going to finish up after this. I won't go through this in too much detail. We like to study the lithium diffusion properties of these materials in great detail. And the reason for that is we can understand how the lithium ions are moving. We might be able to engineer those structures a little better so that it's got an easier passageway through the material. There's lots of ways to study lithium mobility. You can use impedance spectroscopy, you can use NMR, you can use sort of galvanostatic type of experiments. But what this sort of graph is hopefully showing is for even in a single type of material, here is just lithium iron phosphate, I've got a huge change in the reported values for lithium diffusion in the literature. And that's because there's no standard way of doing an impedance measurement for the battery community. Each user might do it slightly differently, and they may press the pellet slightly differently. And every time you press the pellet, your brains to interact with each other. And every time they interact, you've got a new interface that is going to be a challenge for lithium ions to get across. So we've turned to antimatter, which is quite exciting, and it is. We use muons to interrogate lithium diffusion. So we go down to the ISIS muon and muon facility, that's these buildings here, right next to the diamond synchrotron for X-rays. And we use their muons. What's a muon? A muon is a positively charged particle that has a spin associated with it. They're naturally, they occur in the atmosphere. What we do is we embed these muons into our material, and they sort of sit within the material and act almost like a lighthouse. They're looking around at what's happening. And because they have a spin, anything that moves nearby can change the orientation of that spin. So if a lithium ion moves nearby, that spin can change. And what happens is after about 2 microseconds, the muon dies and it emits something called a positron in the direction the spin was pointing just before the muon died. What's it? Decayed. It's more correct. So it's a very sad experiment, but we collect all those positrons. They tell us what happened to the muon. That tells us what was nearby, and we can work out what the lithium diffusion properties are of that material. And what we've been doing increasingly in Sheffield, I'm not going to go through this, is we've been developing new methods at the ICIS neutron and muon facility for not just studying the diffusion properties of the powder material. We've actually built battery cells that you can put on that muon beamline, and you can start to interrogate what happens in solid state batteries when lithium metal is reacting with your electrolyte, forming additional phases. You can also look at what happens to lithium diffusion coefficients as you charge and discharge a battery. That's just what this graph here is showing you. So I'm going to wrap up and just tell you what we're planning in the next few months. We're going to keep working on some of these ways of interrogating material and learning their properties so we can design better materials. We want to try to make things much more sustainable. So we're looking at ways in which we can measure the energy demand for synthesis and how we could try and drive that down and use smarter materials, smarter liquids, for example, in some of our liquid-based syntheses. Can they help us drive down reaction temperatures? So looking at things like ionic liquids or deep eutectic solvents, being able to access temperatures we otherwise wouldn't be able to get to. We're also trying to understand the nature of coatings and interfaces and how they can be manipulated to get faster ion transport. And this project is just starting in Sheffield on sustainable microwave manufacturing of functional materials. So this is a collection of researchers across chemical engineering, material science and engineering, automated control engineering, and chemistry to try to look at how we can come up with some continuous manufacturing processes for battery cathodes. So with that, I'll just say, oh, I've just one last thing to tell people, sorry. If any of you have school kids or know of school kids who you think might be interested in learning more about batteries, is Katie here? She is about to like completely mortify her. Katie was a summer student with the FutureCat project, and Katie did this really cool thing where she made a card game for secondary school students who can then play this card game and come up with routes to making or building their own battery. And they have to sort of make decisions along the way of safety, cost, cyclability, sustainability. So it's teaching people, okay, you might want everything to be sustainable, but you might not be able to have it. So what sort of decisions will you make along the way? And the other thing then was, I'd set this up in the summer, just coming back from COVID, the recharge network for anyone in the research community who has caring responsibilities and coming back from COVID, it being so challenging. If you want an online cup of coffee, you can join that network and just meet other people who are doing the same thing. So there's quite a lot of academics on this. These are my 2 little monkeys at home. And it's nice to have a cup of coffee and a chat with other people who are doing the same thing. So just to acknowledge all the people who did the work, particularly Beth Johnston, who's the postdoc in my research group at Innocent Island, is also a postdoc. My lovely husband and my favourite collaborator, Eddie Cussen, who does lots of work with solid electrolytes. Lots of collaborators around the UK and funding agencies, and thank you so much for giving me the chance to share some of this with you today. I hope it's been okay, and I'm really looking forward to answering any questions that you might have. Thank you.
So thanks for that. Absolutely fascinating. Never ceases to amaze me what's going on in Sheffield. Some of the issues you're addressing about batteries having longevity, more sustainability is something that needs to be tackled as we're head on into the world of electrification for sure. So we've got time for a few quick questions, I guess. So I don't know if anybody's got anything specific. I'll pass the mic to you.
You mentioned the problems with cobalt and batteries. sourced in fairly unfriendly parts of Africa with no child labour around. When we've all got electric cars, there's going to be a huge demand for lithium, unless we can find something else. And lithium is not mined in anything like the quantities that it will be required in 30, 40 years' time. And it's very much Chinese controlled. Is it likely that we can find an alternative to lithium?
So I agree that we have to have an alternative to lithium, because you're right, the demand for lithium will be enormous. And whether or not we even have the reserves to meet that demand globally is a question. I think that sodium is a fantastic alternative to lithium ion. And I think that it could find quite a big penetration into electric vehicle markets. I think as well for stationary storage that sodium ion could be really useful as well. I also think that we have to do quite a lot of work on recycling and recovering lithium from existing battery packs, because at the moment that just isn't happening. And so it's starting to happen, but not at the rate that what we can do now. If you look at stuff like sodium ion or solid state batteries, what we should be doing is, from the moment we start discovering this stuff, we should be learning about how to retrieve it at the end of its life as well, to get ahead of what we've learned from lithium ion. But I completely agree with you that we have to have alternatives to lithium ion. But for the next 20 years, I think we will have a reliance on lithium ion for electric vehicles. And then as sodium becomes more more understood, and we settle in on a winning sodium cathode, for example, I think you'll see greater use of sodium ion batteries.
Are you familiar with the work that's going on at, I think it's the University of Queensland, where graphene is starting to be seriously considered?
Yeah, there's lots of work being done on two-dimensional materials, because their potential to store large amounts of energy. And being able to do it at scale is quite a challenge. And being able to do it reproducibly can be a challenge. But there's so many. One of the things that I'm always cautious about is picking an individual winner. I don't think there is one. I think that the future is going to look really a bit like the Mary Rose Wood, right? Very heterogeneous. I think that's quite exciting. So I don't think everything will rely on lithium ion batteries or sodium. I think there's potential fuel cells, there's redox flow batteries, there's how you then sort of interact those with renewables. And I don't think there's going to be sort of a silver bullet or one size fits all. So yeah, I agree. And for that reason, I think that graph that shows the decisions that we're making today affect us 30 years down the road. We have to be doing as much fundamental discoveries today so that we've got the most choice for what those potential applications might be in the future.
Any more questions?
I don't know very much about batteries. So when you were talking about the sodium placement and how you snatched all that stage work, you talked about that was close to theoretical capacity. How close is that capacity to standard batteries now? So I'm not sure how far off it is.
That's a really good question. So for sodium ion, our capacities they're slightly lower than lithium ion. And so that is a challenge at the moment. And the material I showed you that's not like the one cathode that you can use. There's many, many other cathodes. So the question you have about capacity is really important. The way we're trying to address it is we're looking at other crystal structures where you can actually fit more lithium ions in forming the unit. So we're looking at things like Weberite structures, which don't have oxygen in them, they've got fluorine instead. And you can fit up to 3 sodium ions forming the unit. And that gets you closer and closer to the sorts of capacity that you're seeing with lithium ion. But it's a really good point. The other thing though about sodium that's really nice is you can actually transport it at 0 volts. You can't do that with lithium ion batteries. It's really difficult to transport as a safety concern. Sodium, you get over that challenge. So this, again, like the card game, you've got these trade-offs And so it's about deciding what's best for the application you want to use it for.
Yeah, one question online.
Yeah.
Serena, I want to take you back to the Mary Rose and to ask about one of the objectives. So you're doing these fantastic treatment methods, but is the goal to treat everything that's left or just to see a small section of it? Because that's going to be a big job.
That's a brilliant question. So I think that the reality for this is spot treatment. So where you have very high concentration of iron deposits. And when you go to see the Mary Rose, you'll see where in her hull there would have been an iron bolt, for example, because you can see the weeping of oxidized iron down the side of the ship. And so this kind of magnetic nanoparticle treatment with the gel could potentially treat that particular spot. What we're trying to learn a little bit more is how far into the wood are the particles going? Are they actually reaching the parts where we've seen nanoparticles of iron sulfides? So our next experiment, we've applied for time to go back to France to look to see what happens. But I can tell you, and I've got to tell you that I was pregnant in that photo. It took a long time to go through the data. It didn't take 6 years, but it did take a few years between kids. But hopefully we'll get the answer a bit faster.
Yeah, I think we're just out of time, so just want to say thank you once again. It's been absolutely fascinating. I guess in terms of sustainability, the interesting thing is in 500 years' time, then everybody will look at anything we've left behind. That's an interesting topic for another discussion. So once again, thank you very much. Absolutely fascinating. So, put the hands together.